We're Team Holeshot. Our project is a boat propeller. I'm Tanner Obeck.
I'm Josh Metlock.
Justin Walkup.
Zach Qualls.
Brian Platts. William Fitzgerald.
So the overview of our project is to make a dual rotating boat propeller, and the advantages to our boat propeller versus dual propellers that are already out there is ours are not counter-rotating. They're actually two separate propellers that are key locked together. The advantage of that is you can use the standard prop shaft that come on every boat engine. You don't have to buy a new lower unit with a longer prop shaft. If something does happen to one propeller, you can replace one propeller without replacing the other propeller, and it pretty much saves you $3,000 in cost instead of buying the lower unit and the propeller that's already out there on the market right now. Another advantage is that you can change the props while you're out there on the water, not having to deal with the lower unit and having to take it into the shop, which is going to drive cost up.
Now the tasks for the job were basically for research on ways, research propeller to actually compare with boat performance, develop design to allow use for the propeller on outboard motors, and optimize the properties of the propeller that we have for the best and increased performance. Then we begin to manufacture it, and then we test it both in some form of software, such as working models, and as well comparing it to actual testing of the prop motor. For the benefits, it would actually improve fuel efficiency and reduce drag on the engine and to the boat, bring the boat to plane faster, which will cause an increase in thrust, and what the benefit of that would actually bring is it allows it to go into other bodies of water, basically shallow bodies of water.
One of the main things about the shallower bodies of water is the composition of the bottom that you're on, whether it's sand, mud, grass, or an oyster reef. Greatly depends on the performance of this prop. Mud is going to be your best option because you're able to get the boat moving. Sand's kind of hard, it doesn't really move that much. It kind of just pushes the water around, where that mud will kind of move around that prop and grab better and have you better pull shot to get on plane faster.
So the planning, our original plan was to create the 3D model first, and that is complete. Here, as Tanner was saying, our propeller is a two-piece design that interlocks together. That way, if you need to make modifications to it, it's easier to do it that way. This is the lead prop of our design. We didn't get a screenshot of the trailing prop, but it's very similar, and you can see the keyway interlocks in there. The next step was to create a 3D printed model, which we have done. Our mentor has it right now. We're working on the manufacturing as well. It should be done within the next few weeks, and after that we can go on to testing the propeller on an actual boat. For the design, these are the different properties that we have to look into, or we had to look into when we were creating our prop. The pitch, rake, diameter, cupping, and number of blades, they all are taken into account when you're talking about the performance of a boat. And it really depends on the boat a lot, because different holes and different shapes are going to require different parameters. So with these designs, the pitch, we put the two props are a little bit different in the way that they're shaped and sized, just to allow for better, more fluid flow, the water coming through it. The pitch on the lead prop is 22 inches, while the pitch on the trailing prop is 26 inches. The rake is 31 on the lead, while the trailing prop is 35 inches. The diameter is 15 inches on the lead prop and 14.25 on the trailing prop. And both the lead and the trailing prop have 3 blades that are offset.
One of the main reasons for the 3 blades is you have your prop shaft on a normal engine that's set up for a single prop. When you add 2 props, you add a lot of weight. When you try to put power to that, the torque trying to move that much weight, there's a problem with it bending or cracking the prop shaft itself. So what we had to do is figure out how to make that two props light enough to where we're not breaking the prop shaft every time. We have to either figure out how to make them lighter, which is why we went to 3 blades instead of 4 to save mass, and that in turn helps us to where we're not breaking prop shafts whenever we're putting throttle to the boat propeller.
And then with all of these parameters that we just mentioned, we're able to go in and model our design. The reason we wanted to model is because it allows us to make easy design changes. So if we wanted to change any of the parameters we just mentioned, it would be fairly easy to go in and change it. Whereas if we decided on a parameter, manufactured all the way through, tested it, decided it didn't work out, it would be a lot more work to go back and redo all that. It also allows us the opportunity to 3D print it. The 3D printing is nice because it allows us to test fit on the boat to make sure that everything physically fits. Obviously you don't want to go through making the whole thing, having it cast, and then finding out it doesn't actually fit. It also helps out with the manufacturing aspect because it helps with the mold making process. So when we do go to have it cast, it's a lot easier to get that mold made with 3D print as opposed to just making the mold from scratch. And then it also, having that model, the drawing in 3D helps us to do flow simulation, which will help us do comparison between the traditional prop and our design to confirm that our design did improve performance.
For manufacturing, our final prop, we want it to be stainless steel prop 15-5. Stainless steel because less likely to corrode, and the 15-5 because it's a harder stainless steel versus others. For the 3D printed design, like Brian said, it is complete. Our mentor is using it, showing other clients, and he's trying to get a mold out of that. And then
so the materials we chose for the 15-5 stainless steel, we used the round tube stock so that we could use that to bore into the mold and create the propeller. Funding for our project came from our sponsor, Chuck. Second part of our cost, that'll come from the creation of the mold and the casting of our propeller. And then once our 3D printed prop is complete, manufacturer will use it to create a mold, cast our prop. The projected cost is $200 for this process.
We're gonna get them casted out of house, so I'm not exactly sure who he's taking it to cast the propeller. He hasn't let us know that information yet, but he's gonna get them cast, and we're gonna try to get the details on how long that's gonna take and the money he's putting into that, so we have it for our project.
for testing, again, we do SolidWorks. Hopefully we can get through the school so we can come on campus and get the whole flow simulation done with that. And then the next step after the flow simulation is putting it on an actual boat. Again, we had decided to go with a smaller boat, V-hull, 19-foot blue wave, and we're going to mainly be looking timing on the planing speed and as far as the depth of the water, what we can possibly get up to and run it.
These are the websites that we use.